My name is Kirk Shoop, and I work at Microsoft. I've been, not as a part of my job, but on my own, I've been building a library called Reactive Extensions for C++, RxCpp. And the core idea in the RxCpp library is algorithms, it turns out. And this talk is going to be about how these algorithms are different from the algorithms that are already in the STL and the algorithms that are being added. So it doesn't really match the types of algorithms that you use for parallel, and it doesn't really match the types of algorithms that you use for sequences in space over collections or things like that. I much prefer discussion to presentation, so I will be very welcoming of questions as we go through all of these design options, because eventually I think these algorithms also need to be added to the standard. And so this will kind of talk about what I think these algorithms need in order to function, and the kinds of design options that you would go through to try and build these algorithms into the standard. And then, of course, I have the most familiarity with reactive extensions, so a lot of it will kind of look like the reactive extensions, but I will try and cover a couple of other libraries near the end. This is an example of an algorithm, and these are marble diagrams. So this line represents input to the algorithm, and this line represents the output from the algorithm. These are termination lines when the stream ends. And then, space is time in this case. So one of the differences when you're dealing with this set of algorithms is that instead of the values being distributed in space, say in a vector or a list or something like that, they're distributed in time. And things that are distributed in time can include mouse clicks or network packets or file I/O. Just about everything that we actually deal with in modern programming has an asynchronous aspect to it, whether or not we actually use asynchronous code or algorithms to process them. And so this particular one is debounce. So if you had some input like mouse buttons or keyboard clicks or some other switch, and you wanted to debounce them so that you were only getting outputs when you didn't have a cluster that was too close together, right there I've moved 5 far enough forward in time that 4 becomes a value in the output stream. And if I move it back, 4 disappears. These diagrams are all on rxmarbles.com. In fact, this whole presentation is being hosted by my GitHub repo. This is on GitHub, and I have a website published from it. So if you go to Kirkshoop, one word, .github.io.com/CPP Russia 2016, you can go and do this yourself and play around with the slides while I'm talking, or later. So this is an example of a composition of some async algorithms: concat map, group by, flat map. So in general, what this is doing is it's taking in a series of lines of bytes from, you could assume, a network. And every time there's a 13, it represents the end of a message. And so when a 13 arrived, see this arrived, and there was no 13 in it, so nothing was output. So these lines are the input bytes, these lines are the outputs. And so as soon as we had received a message that had a 13 in it, we were able to print all of the collected A's and all of the collected B's as 2 separate messages. And so this is your async read byte source. I'll pause just a minute to explain the output. All of this is real C++ code on that GitHub repository, compiled with the Emscripten compiler, and the JS result of that compilation is running in the slides. So if I go back and forward, we'll get different results because I'm randomly producing these byte streams. And what I've done for dramatic effect is I've said that the async read bytes is producing a line of input bytes once a second, which is why the whole thing progresses fairly slowly and fills out. The tap is kind of like a faucet in a pipe. You get to inspect the contents of the stream as they're coming through. So that's how I'm printing out the input that's coming from async read bytes. And then we take a function called vector of strings from vector of bytes and pass it to concat map. And it takes those bytes that came in and turns it into a vector of strings split on the 13. So in that first line, there's no 13, so it comes out as a single vector. The second line has a 13 in the middle, so it comes out as a vector that includes the 13 and a vector that doesn't. That's all that the concat map is doing, is it's taking and splitting by the carriage return, the 13. The group by is saying take a group from the string. It's another function. And what it does is it says, when you see a 13, that's a new group. That's the end of the old group. We're going to return a new group now. And by doing that, I can say that the vector that was produced by this one and the vector that was produced by this one are part of one group, but this is part of the next group, and so is that. But then again, I switch groups and go here. So now I have groups that are related to messages, but each of those groups contains more than one vector. So that's where we fix it with flat map. That takes a function, append group strings, and it says, because what the group produced were these groups, it says for each group, that's what the next one does, for each group, concatenate all of those into one string. And so once I've done that, I can print out one string, one string, one string. So has anyone seen Sean Parent's talk about avoiding for loops? It's a very good talk, I thought. I've noticed myself in code reviews now, every time I see a for loop, I end up entering a comment in the talk, in the code review that says, well, that for loop is actually a filter and a transform, or a copy if and a transform, or a rotate, or whatever. And it ends up being something that changes the code so that you're not re-implementing algorithms over and over again. You're just reusing the ones that were already provided for us. These algorithms are kind of the same way. We write these types of algorithms all the time for async programming, but it's all spread out across callbacks and stateful objects, and they're all re-implementing the same thing, and they're all using these primitives of mutexes and threads, which are what are available to us, but which are not only difficult to use correctly, they're also difficult to use. It's a trade-off between correctness and performance sometimes, and the farther we push for performance, the harder it is to maintain correctness. And so just like the linker provides this opportunity for a few people in the world to sit down and figure out what assembly should come out of our code, it's also useful for the STL to sit down and build the algorithms that we can use over sequences in space. It seems pretty obvious once we've decided what the algorithm set is that we need in the asynchronous space that it would be useful to have that implemented once. and then use that instead of raw callbacks, threads, mutexes, etc. So this is another demo. In this case, we're looking at more of a UI scenario. I said that mouse clicks and moves are sources of values that are spaced in time. And so here we have mouse downs from window. Again, I'm using Emscripten, and Emscripten lets me actually hook up to the DOM. So these are actual window events from the DOM on the slide. And so you can get all the mouse downs, you can get all the mouse ups, and you can get all the mouse moves. And then you can say, whenever we get a mouse down, here it is, but we don't really care about the mouse down. What we care about is the mouse moves. So for every move during this mouse down, stop those moves on the next mouse up. So we're only collecting moves between a mouse down and a mouse up. So drag events, essentially, moves during a drag. And then I map from the mouse event, because I don't really care about that data, to 1, to just an integer 1. And I start with 0 and I sum. So right there I've said, keep a count of the number of mouse moves that occur between a mouse down and a mouse up. And now I can turn that count into a string and print it out. So again, I can build this, I can use this flat map, the same flat map that we used before, only this time you can actually see the function that I'm passing to it. Because the other slide, the functions were a bit long, I didn't show them. But now you can actually see this function that's being passed to it. And what it does is it returns a new stream. And in this case, it starts out as being a stream of mouse events that are move events that will stop on the mouse up. But I turn it into a stream of integers starting with 0 and tell it to add them all up. Do we have microphones? I know we usually wait till end, but I'm perfectly happy to.
Wait.
Why did I capture by value? These are slides. So, no particular reason. Yeah, the caller, of course, owns it, and the caller doesn't go away until this function returns. So I can just as easily pass a constref. It's just whatever I decide to put into my flat map. Sometimes you're dealing with things that are very lightweight, and so you can just take them by value. But yeah, in general, you would use the same practices that you would use for regular functions. Oh, that's too bad. Try it again. Well, that's sad. So on my machine, it worked. So yeah, maybe on your machines it works too. I don't know. You can try later. So this is a different type of source. Again, I'm using the Emscripten hooks to the DOM. So this actually builds an XML HTTP request that I pass this URL that in the real code doesn't have ... That's for the slides. And again, we just flat map the response, which has both a progress stream and a load stream. The progress stream has a number of bytes downloaded as of now in each value in the stream. And the load stream will fire at the end with the actual contents of the response, of the file being downloaded. And then this was going to download that file and display the first line of it. And so you would have seen the numbers count up, and then you would have seen the first line of the file, which was actually, I Googled how to say hello in Russian, and that's what it was supposed to be. Oh well. So those are the two streams. These highlighted algorithms provide, when used in this way, provide a fairly common pattern. I don't know if anyone is familiar with Reflux, which is a JavaScript library in the UI space, kind of the Flux architecture. But essentially what you have here is you've defined your data and you defined your model, which is a map of URLs to data, and the data is holding the first line of the content and the size that's been downloaded so far. So you've got these simple little structs, no methods, no complications, they're just structs. And these become your state, but you don't care about any of the complexities of maintaining state in an asynchronous system. That's handled by these algorithms. So for instance, I can combine the latest value of the progress and the load. By combining them, what I'm saying is that I have two input streams over time. And once I have a value in each stream, every time any stream gets a new value, I get a new output that that was the result of this function being called with the new values. So combine latest always stores the latest value from each stream, and every time a value changes in either stream, it calls this function with those two values and produces an output. So this allows you to take several different sources of values over time and combine them into a single set of combined values. And once you've done that, you can go to scan. And scan takes the output of the function, which was a tuple of the URL, the progress, and the data, the result of the download. And it takes initially an empty model, nothing in it. And then it takes this function, which was too long to put on the slide, sadly, called update model from tuple, which just takes the URL and uses that to index into the store, and then sets the size from the progress object and the first line from the data object, if it's there, if there's anything in it. And then what scan does is every time it gets an update, it calls this function, and then the result of that function is what gets passed out. So scan is returning models over time, over and over again, but the data in that model keeps getting updated every time before it gets emitted. So for instance, this is the scan. For every input, there's an immediate output that is the result of the function. And in this case, it's doing a sum. But it's always storing the result of the function to pass in as x next time. So the result of the function becomes the new x that scan stores. And that's why it becomes a continually updating. It maintains state for you in a way that you don't need to do on your own with, again, mutexes or anything like that. Whoops. And then, sure, it's a nice pause. We've kind of looked at some of the ways you can compose algorithms, some of the algorithms you can use, what benefits you get from them. I don't know if you noticed, but there weren't any loops. There weren't any callbacks in the normal sense. There weren't any mutexes. There weren't any threads. It was extremely simple compared to most things when you're trying to coordinate these asynchronous strings. By the way, that's Bilbo's house from Hobbiton in New Zealand. It's actually a place you can visit. It's kind of fun. We got more out of it than we thought we would. So, why algorithms? They're documented. They're stable. Someone wrote them. They're optimized. Someone spent some time testing them and making sure that they handle a variety of cases. They're descriptive. So when you read your code, you don't just see a whole bunch of callbacks with a whole bunch of variables scattered around that are trying to coordinate some action. You see something like group by, which kind of tells you, I'm going to create some groups here. So, algorithms operate on sequences. By the way, this is why future isn't, in my opinion, a sufficient abstraction for building algorithms over time, values over time. Futures are a representation of a single value. We have those in the languages, that are in the regular language, like without async as well, just an int on the stack or on the heap. That's also a value. But it's kind of hard to build an algorithm over an int. Algorithms really become useful when you have a vector events or a list events or some other generator events, something that actually produces multiple values in a sequence. Same thing here. We will get the real power out of algorithms in the async space if we can find a way to abstract the values arriving over time. So yeah, that was supposed to be a MathJax diagram of an array to show values in space. Again, worked on my machine, I don't know. So if you have a vector of a tuple of ints, you could call that mouse moves. It's useful in some scenarios, but in a real app, it's not that useful because it's in space, not in time. It's not actually a reflection of how the actual device operates. And you can build generators, which are another form of space. And this is using co-yield, as Gore talked about yesterday. These generators may feel like they're not operating on values in space, but I contend that they actually are. There's nothing particularly asynchronous about this. It just doesn't actually store the values in a lot of space. It stores it in the state of position so that, the next time you come in, it gives you the next value. Versus time. In this case, again, looking at the way these things might be visualized or implemented in a library using the await proposal. You could have, on a window object, a mouse move method that returns an async generator of those positions. And then you would await the generator for all events, the async generator for all events, and filter out any events that were mouse moves, and then yield each of those events. It's one way you could imagine doing that in a wait world, and it does represent a stream that is purely asynchronous. You can do the same thing with bytes, where you do reads from some underlying API, like the one that Gore showed us the other day, for reading from a socket. You could await that read and then yield out that byte and end up with a source of all the bytes, so that you've basically just hidden the while loop away. In a sense, it becomes kind of an algorithm. But in general, the idea here is that you would prefer sources that represent a sequence of values over time to writing loops over things that return a single value at a time. So when building something like this, you have to make a series of decisions. Are you going to abstract the sequence, or are you going to abstract the algorithm? I've only seen one example of this, abstracting the algorithm, and I haven't tried to actually figure out if it would work in the async space. It's called transducers. I don't know if anyone's heard of transducers. Cool. So Rich Hickey in the Clojure community, he devised this pattern called transducers. It's essentially an STL algorithm set where you implement an algorithm by implementing the step function for a reduce. Is everyone familiar with the reduce? It's just standard accumulate. Yeah. And so the step function that you pass into that, accumulate, can actually be an implementation of a transform, or it can be an implementation of a filter, or it can be an implementation of most of the other algorithms that are already in the STL. And it turns out that you can abstract the algorithms rather than the sequence. And so what you end up doing and there's slides at the end where I'll go into this in more detail, but you end up, I probably should just stop with it abstracts the algorithm. It's a very interesting idea. Everything else we have abstracts the sequence. We have iterators. I'm going to show like senders and receivers and observer, observable. So I found that very interesting, and I would like to spend some more time looking at that. So that's one of the decisions you have to make. Then you have to decide push or pull. So push feels more natural in an async space. It feels weird to pull the next value before it arrives, to me. It feels more natural to have given something a function and told it to push me by calling that function the value when it arrives. But there are both options, and in fact, if you built these algorithms directly on top of the await proposal, that would be a pull version of this. Because you would be actually setting up a async for loop over your source, your async generator source, and looping through each of those things by awaiting the next iterator. And that's a pull operation. So I also want to explore more of that than I have yet done. I've been working more in the push space with RxCPP and this presentation. Another decision you have to make is, how do you cancel? You don't really get to decide whether you cancel. You just have to be able to cancel when you're dealing with async things. That earlier slide where there was a mouse down, mouse move, take until, mouse up. Without cancel, take until doesn't work. There's no way for me to shut down the source and unwind the whole thing on the mouse up unless I can tell every stage in the algorithm above me, you're done now until the next mouse down. But you can do it either by omission, which is essentially, again, what you would see. That's usually paired with pull. So if I'm doing a for loop over an async generator in the await syntax or proposal, and I break out of that for loop, my cancel is essentially waiting for the destructor to run on the async generator so that it shuts down everything. Maybe there's a better way to do it. Again, I have to explore that more. Versus trigger, which is when you actually have some sort of shared object. It imposes this requirement because both the algorithms need to be able to stop, and the subscribed object, the thing that connected in the push model, the thing that connected a receiver to a sender or an observer to an observable, needs to be able to tell it, yeah, I connected you, I was interested in your stuff for a while, but now, not so much anymore, you can stop now. And so that trigger needs, you need one of them, essentially, to be able to stop things. Implied in this cancellation is this concept of an asynchronous lifetime. And we'll be seeing more about that later, too, where you have this thing that you start, and then sometime later you stop, and the lifetime of that thing is asynchronous. And then the last thing that's become kind of important is how you chain algorithms. So the STL, as it was in the beginning, doesn't really support nesting of any kind. It's pretty awkward to get the results of one algorithm and pass them to the next because of the separate iterators. The range proposal is what was fixing that. The range is a pair of iterators, and so now these are very composable, and because of that, the range proposal chose operator pipe to be the thing that would chain multiple operators together for you. I'm using that in the slides. The RxCpp library today supports dot syntax on a source. So all of the functions are actually represented as members. I liked it that way to begin with because it helps a lot with IntelliSense. If you type dot, suddenly you get a list of all the methods you can call, all the operators you can call. But it seems to be that people are going for operator or, and after having worked with RxCpp for a couple of years, it makes sense. There are a whole bunch of circular dependencies that end up coming in when you have your algorithms in your observable as a set of members that are a nightmare for both the maintainer and the compiler. Function nesting, the transducer library works that way by default, although I do believe when I did build a little transducer prototype in C++, I was able to chain them using an operator, pipe operator. But by default, the pattern that Rich Hickey proposed was function nesting. So you end up calling a function that is taking as an argument the result of some other function, et cetera. And so all those functions nest together. You end up with a whole bunch of parentheses and matching parentheses. And in general, the operator approach is a little more usable and readable, I think. So let's spend a little bit of time assuming that we're going to abstract the sequence. It's going to be a push flow. We're going to trigger for cancel, and we're going to chain using the operator pipe. Some hot springs. be nice to relax for a bit. So I built a toy implementation, single header file, on that GitHub repository. It is not completely correct. It is not complete to begin with. But it lets us go through some slides where we actually build from first principles. Looks like too much. It's not really that hard. You've got a sender that takes a receiver. It's a fairly normal, like a signal slot or the classic gang of four observer pattern, a visitor pattern, all sort of the same stuff. This thing of an algorithm, it's just when you have a function that takes a sender and returns another sender. It built a new sender doing some extra work and calling through, like adapting. It's an adapter from a algorithm from a pattern perspective. Lifter is another adapter, but it adapts receivers instead of senders. So you can build another receiver out of an existing receiver. And then a receiver is just something that has a function that takes a value. It's all very simple. And you can build, thanks to C++14, things that fit on a slide that implement these things. So this is a sender called ints that will send the first int to the last int by doing a for loop and calling the receiver. Because what it did is when you called ints with the range, it returned you a new function that would take a receiver later. And when you give it the receiver, then it actually calls that receiver with each one. Very simple, not that bad. And then you have copy if. We already have that in the library. It takes a predicate, and it returns a function that also takes a receiver. Sorry. Copy if is a lifter. So it returns a function that takes a receiver and returns a receiver. And so once you've given it, given this new receiver to someone that's going to provide a final destination, then for every value you check the predicate and you only pass it to the destination if it matches the predicate. So a very simple copy if algorithm that only sends it through to the next receiver if it matches the predicate that you gave it when you created it. Print2 is your final receiver. It's just a receiver. It returns you a function that whenever you pass it a value, it prints it out to cout. Well, in this case, because I would pass in cout as the stream. And then this is just a simple little function that we can use as a predicate for copyif that only returns true for even numbers. So given that simple definition, you can build this. And that's function nesting. Not so pretty, not so easy to read, lots of parentheses. If you like Lisp, maybe you like this better. Or you can do the same thing after you add the operator support. A little easier to read, a lot less parentheses. But it is not sufficient to produce this algorithm. This algorithm only remembers the most recent value in its state that was received. And only when the original stream ends does it output the last value that it had stored. Now the issue here is that that model that we just went through does not tell an algorithm when it ends. There is no signal for this thing has stopped. It's the reason why signals and slots don't really model something that the algorithms can use to do their work. It's the beginning of the reasons. So in order to do this, we have to find a way to send an end signal through. To make an analogy to the STL, the end signal in the asynchronous realm is essentially the same as saying, does the begin iterator equal the end iterator? Iterators would not be very useful without that comparison. We have to be able to know when we've hit the end. So here's the last or default implementation, and it calls end, which is a new method that we had to add to the receiver. So now the receiver has two methods. And so last or default will take a default value and return a function that takes a destination, and then it will store that default value as state, and it will make a new receiver to return. This is a lift implementation of an algorithm for an algorithm lifter. So it takes a destination and returns a new receiver that can then be used to send values to or to send completion to. And what happens is when you send a value to it, it stores it in its state. And when you tell it to stop, you tell it it's over, then you emit that last value finally to the destination and then tell the destination to stop as well. Make sense? That allows this. What we're seeing here is 100 million ints are produced. And remember, this is a JavaScript running this live. That's how fast it did it. 100 million ints. But we filter it down to 50 million even ints, and then we just take the last, or if there were no events, we return 42. We didn't return 42, so we got some events. And then you print that to see out. What I've done in this toy implementation is I've given a sense of the lifetime, the asynchronous lifetime that I was talking about before. There's different phases to one of these. You have a construction phase where you're constructing each of these objects. And then you have a connection phase or a subscription phase where you're processing the pipe operators to connect all of those receivers. Like this receiver ends up getting passed to this, and then this receiver ends up getting passed to this, and this receiver gets up passed to this, and now you've got a whole chain. So first we make a new ints, we make a new copyIf, we make a new last or default, we make a new print2, and it's the one that defines this lifetime object that knows about cancellation and lifetime for state within the stream and so on. Only after that do we find that last or default is bound to its destination, which is print2, and then copyIf is bound to last or default, and then ints is bound to copy. So we have different directions here, if you hadn't noticed. We start at the top and we construct everything. Then we start at the bottom and we connect everything. And then once we get back to the top, it sends all the values out. So all the values came out, we got the result, and then we print done. And then stopped and destructed are about this lifetime again. Those are the scope operations that you would expect from something that was managing lifetime for you, like destructor on the stack or unique pointer, shared pointer, etc. But we're not done. Completion's all nice and fine. But here's another algorithm. This one says, I only want to take the first two values, and even though this stream continues and continues, I'm not going to pay any attention to it. I'm just going to stop now. This is the one that requires cancellation. This is the one where I need to say stop processing even though the source isn't done yet. And so we start talking about the subscription and adding that to the receiver so that we can have a lifetime. Adding it to the receiver is not quite correct, but it's what I'm doing for this demo. The RxCPP itself does it a bit differently. So we'll talk about the subscription very quickly. You can ask if the lifetime is in scope by using isStopped. You can stop the stream by calling stop, and then you have this way of nesting scopes. So you can insert and remove scopes for nested scopes. And you can get notified by passing a function into this when a stop has occurred, so that you can perform cleanup operations. Sometimes these asynchronous things have actually circular references, and so you break your circular references using things like this. And then this allows you to create heap allocated objects that are scoped to the asynchronous lifetime. So you don't have to build a separate shared, the RxCPP doesn't have this cute little feature. And so RxCPP ends up building a lot of shared pointers and different algorithms to hold the state for each algorithm. And I don't like it, and I want to fix it. And when I was building this, I figured this out, and I'll try and get it back into RxCPP at some point. This way, all of your algorithms don't have to deal about the lifetime of their state. They just ask the subscription to handle the lifetime for them. Oh, and then that's the implementation of take, which is just use the destination's lifetime and to make a state variable for the number of things that are remaining to take from the source stream, and make a new receiver. This is another lifter implementation. Make a new receiver that calls through to dest by default and passes the state around, and then you get the dest here, the state here, and the new value. And so if the remaining after it's decremented, before it's decremented is equal to 0. No, after it's decremented is equal to 0. Which is that? It's the problem with talking. You think much better when you're coding. Anyhow, when that reaches 0, you're going to tell it to end the stream. And if it hasn't reached 0 yet, you go ahead and pass the value through. So again, not that complicated, but without the ability, and it's kind of hidden. Sorry, it's hidden here, the lifetime, how the lifetime is controlled to cancel. There's a contract on completion. When you call the completion method on a destination, after it finishes, it stops the chain. Completion is a terminator. But in order for that to work, you had to actually have the subscription in the receiver so that you could actually have the call to the termination function call stop after it ran. So that ends up canceling it. So now you can do take 3. And so even though the async ints was supposed to go from 0 to 9, we end up stopping after 3 even numbers. And that's another interesting thing, is we don't stop after, because take is after the filter, so that we're only seeing even numbers, it's the 3rd even number that stops the stream. Yeah, I know. More changes. So what do we have to do to support failure? These sources can fail, especially if we're talking about network requests. I mean, you saw one earlier, the HTTP GET failed for some reason. And so that failure has to be represented in the stream. It's also a terminating condition for a stream. So we add another function to the receiver. So now we can take values, we can take exception pointers, and we can take completion. Either of these functions will terminate the whole string as soon as they've returned. That is part of the contract. So now we can have a function that looks like a predicate, but doesn't actually do anything but throw. And it throws a standard runtime error with a what of always throw. And print to and take past that, essentially copyif is the one that ended up catching the exception and turning it into an exception pointer and calling the method on take, which called the method on print to, which printed out always throw. And so now we have a way to stop the stream on error. What's even more interesting and not particularly covered in detail in this talk is that now you can have operators that deal with errors. You can have an operator called retry, which is a common one, which will restart the stream every time there's an error. Or you can have catch, which will actually turn an error into, like when an error comes down to a catch, what the catch is a function that takes the exception pointer and returns a new stream to use instead. So the stream you were using is busted, here's the new stream. So that's outside the Weta studios in New Zealand. Incredibly lifelike. Like they have glistening snot and filaments of hair like individually inserted. It's amazing. But there are still things that need to change. Delay is the first method that we've dealt with that deals with time explicitly. Delay will take a number of milliseconds, and every time a value comes in, it will wait that number of milliseconds before it outputs it. And so you end up with this shifted display. So in order to do this, we need some way of scheduling stuff to happen later. Something that is schedulable is essentially a function that has a lifetime and has the thing that it was scheduled on. That's for nested scheduling, so that you can essentially implement iteration or recursion. Hopefully your implementation of a worker will actually derecurse or tail recurse or some other way of keeping it from being messy. So a scheduler is a factory. It just lets you create a worker that has a particular lifetime. A worker is similar to a strand. It has some guarantees. I say it's similar to because I'm not quite convinced yet that the executive proposal can exactly match this, replicate this contract. So one thing that a worker has to be able to report is when its idea of now is. It needs you to be able to schedule things to occur ASAP, essentially, and it needs you to be able to schedule things that will occur in the future. The key point to making an algorithm library testable and have reproducible results is actually implemented by this. So the properties of the worker are that it's a FIFO. But even more than that, it's a FIFO even on a particular time point. So if I schedule 3 things that have the exact same when, the first one goes first at that time, the second one goes second at that time, the third one goes third at that time. And then I'm switching at this point because I'm leaving the toy. The toy served its purpose, it was useful. Like I said, all the code is in one header file on the GitHub project repo. But the complexities involved here, I just couldn't replicate for the slide. I needed to use RxCPP. So now we're looking at a simplified view of the RxCPP model. We still have subscription. It's called unsubscribe instead of stop. It doesn't have the other features. We have observer instead of receiver, and named functions for the 3 things. We have a subscriber, and that's the thing that binds the subscription to the observer, rather than it being directly a member of the observer like it was in the toy. And then we have this observable that takes a subscriber and returns a subscription, returns the lifetime, instead of the sender. So it's just moving words around mostly. So this is something fairly simple. Interval is a source that uses a scheduler in order to produce numbers starting from 1. So 1 is produced, 2 is produced, 3 is produced, 4 is produced, and once a second. So these are actually measured times, not just static strings. They're measured times from when the subscription started. So at 1 second, we produced the number 1, at 2 seconds, 2, etc. This is what prints that out. It's this function print produced. This is what prints out the emitteds, print emitted. And we just say delay by 1500 milliseconds on the same scheduler and take the first 5. And this is what you get out. I don't think I'm taking 5. I think I'm taking 3. That's a mistake in the slides. The code is 3. So, to do that, the real time elapsed for the whole operation was 4.5 seconds. 3 was emitted at 4.5 seconds exactly. 4 was produced and printed here, but it was never emitted because of the take 3. Again, 3. Yeah, so here we go again. So it's possible now to actually distribute things in time, to have algorithms that introduce delays or windows or buffers, chunk things up for you. You can do all of these interesting things now in time. But when you're doing things in time, you saw this thing took 4.5 seconds to finish. If I actually wanted to test this code and wait 4.5 seconds for the test to end, my tests would get infinite. So we need to virtualize time. It's not that bad as it looks if you ignore most of it. Otherwise, it's just as bad as it looks. So this is a worker that has a sense of time, but it's a virtual sense. I can call how far I want it to advance to, or advance by, or sleep for, and I can start. The start method will actually make those calls for me. So it will jump to the next time in the queue as fast as it can. And then recorded is something that will record the event. And to be clear, an event can be a completed or an exception or a value, where we're going to record all of the events that can occur and the time that it occurred at. And then your test scheduler knows how to create one of those new workers, and it knows about this virtual time that's being controlled by the worker. But it also allows you to build these static sources of input. So this makes a list of the same input events that were being emitted by the interval in the previous run with delay. This is exactly what interval was emitting. At 1 second, 1, at 2 seconds, 2, at 3 seconds, 3, at 4 seconds, 4. So I make that, and I tell the worker to start using that interval source and the same set of things that I had before, except I don't subscribe here because the subscription is actually inside start. So here I use another tap to print the emitted this time. That's the only change from the code that was there before. And I even got take 3 on this one. It's accurate. And you'll see that it produces the same stuff, but it took a fraction of a second. To put them next to each other, my test is already done here. Thus, the importance of actually being able to virtualize time. It isn't only for testing, but it's the first thing that or it's the most common thing that you run into wanting to virtualize time for. You can also imagine virtualizing time to do scrubbing through video. Like if you were doing video playing, you might have a virtual time stream that matched your thumb position in the video or something. So I showed how you run the test through start. This is how you evaluate the results. You just build a vector of the outputs that you expected, and then you ask for the actual messages that were received by the start. So if you look at that highlighted res, it's the same thing that was returned from start. So you get the actual messages, and then you just compare them. Are they the same? If so, succeeded. We got exactly what we expected. Otherwise, failed, and now you can print out what you actually got versus what you expected. So that's all you really need in order to be able to test values over time and the code, the expressions that you build out of them. Which again, when you're doing the manual things with callbacks and state, becomes manual, distributed state being munged by all of these callbacks, becomes a lot harder to build something that's testable. That actually is a Joey inside of the pouch. You can only see one leg. So, what designs? We had these decisions that we could make. Here's async generator. It would be the await proposal would build an async generator, or at least someone would build an async generator using the await proposal. And I know I'm supposed to do that, Gore. I'm still planning to get back to it. So the concepts for an async generator, I don't know if everyone remembers Gore's talk about the await proposal. An async generator would be something that had a begin and an end method, and one of them returned an await iterator and one of them returned an async iterator. An await iterator is something that is awaitable, and when it's resumed, it returns an async iterator. So in the end, you end up with two async iterators. One, you have to await begin, but you don't await end. End is in the range specification. End is more of a sentinel iterator. And then async iterator is pretty much just a normal iterator, except that operator ++ also returns an await iterator. So you end up awaiting on begin and awaiting on ++. So essentially, when you're trying to advance to a value, you await. When you're accessing the value, when you're accessing the value of the current async iterator, there's no await involved. You can just access it as many times as you desire. The await already made sure that the value was there. If you were going to implement copyif or filter, it would just be something that took an async generator and returned one. So you do a for co-await on the original input generator. And of course, you have a new predicate that you're going to use to test each value. And only if the value matches the predicate, you yield it out to the resulting async generator. So this is the pull model using await to implement the same copyif function that the push model implemented a while ago. Does anyone prefer this shape? Yeah? Yeah. I obviously need to spend time making sure that this shape can actually encompass the full semantic and contract around Rx. And of course, you want to be able to use operators to chain things together. Nothing new there. SFRP is very different. Anyone familiar with SFRP or FRP in general? Functional reactive programming. Conal Elliott built this as a mathematical denotation structure for describing values over time. SFRP is a C++ implementation by David Senkel. He's done a couple of talks at CPPCon and CPP Now. I recommend them highly. He talks extensively about functional programming in C++, and one of his talks is specifically about SFRP. The idea for SFRP is that you have behaviors, and a behavior is a function that takes a time value as its argument and returns the t, or the r in this case, that it represents, that is valid for the time that was requested. So if you think about your main loop in a game, you would have this while loop, and you would figure out what the current number of milliseconds is, and you'd call the root behavior of a chain of nested behaviors with that millisecond value, and what you would get back is the state that should be represented on your screen for that millisecond value. And that is essentially what's going on here. You would use something like circle follows mouse that takes your mouse position, which is a behavior over a point, and it would use another function called circleat to produce a different point around the mouse position in a circle that was varying in time depending on which millisecond value, which millisecond value was being passed in to the drawing, to the behavior for each iteration of your drawing loop. The curious thing about this particular pattern, it's definitely pull. You're making the call into SFRP, giving it the current time value, and expecting it to come back with the state that you should use for that time value. In this case, a drawing. The thing that's weird about it is when you get to something like mouse position. So the way you end up implementing something like mouse position is you have to store mouse positions between calls, because your mouse position is going to be coming from a system event of some sort. So you're going to have somewhere underneath the drawing, you're going to have something that's getting these mouse positions and storing them in some manner. And you have to decide how to store them. And then when a request comes in for a particular millisecond value, you have to decide how you're going to represent that store as a single value to return. And so it means the difference from a push model and a pull model becomes more evident here, because if I'm not asking for something, I'm going to miss it. It's no longer there. It got replaced by the next mouse move. So there is no way for me to be sure that I actually have a complete sequence. Now that's my personal mental model of this. It's certainly true that the people that are devotees of this particular model think that it's the only rational way to deal with these types of structures of algorithms and values over time. And so by all means, research and figure out what your own position is. Спасибо. Questions?
Raise your hands if you have one.
Hello.
Hello.
Thank you for this interesting talk. And all these blocks you showed us, they seem quite similar to Eric Niebler's ranges.
Yeah.
And am I right that these things are the same but for asynchronous calculations? And how these relate to Eric Niebler's ranges?
Yeah, so definitely I love Eric Niebler's ranges. I think that they're an incredible improvement over the STL, which I already loved. It is definitely true that these are intended to work in an asynchronous space, and I don't believe that the existing range proposal can handle asynchronous algorithms. I don't know how you would do delay without trying to introduce something like async await into them. And maybe that is where we go, is we find some way to integrate async await into them and reuse some of them. But what you might notice in the range algorithms is that there are some new algorithms that weren't available in the STL. I actually don't have one in mind at the moment, but they're in the view section. These view algorithms are kind of like this, where you can stitch them together, and at no point do they replicate the collection. They're just dealing with a single value, passing through them and doing whatever operation they're going to do on that value. But of course, they're doing it in the reverse direction. This is pushing from source to destination, and that one is pulling from destination to source, pulling the value through. But the main difference is whether or not you can actually wait and get the value later without blocking the puller, the thing that's pulling. And to do that, you either need some sort of rewriting capability like await, or you need to switch to something like a push model where you can just not call the function until you've got the value that you want to push into it.
So it's quite an interesting thing because the blocks, the high-level constructs are the same, but the implementation is quite different for synchronous ranges and these asynchronous things. Thank you.
Thank you. Yeah, asynchrony adds a lot of complexity. Cancellation is not trivial.
Hello, thank you very much for your lecture. It was very interesting. I have a question. Is it possible to apply your quite fascinating approach for network processing? I mean, classifying, parsing, and so on. I mean, I'm kind of involved in network research, and your approach seems to be quite applicable to that. Can you give some directions? Thank you.
Yes, I did show more consumption scenarios, consuming HTTP requests and consuming mouse events. It's certainly true that that is completely invertible very easily, so that the events that you're consuming are requests from the network, and then it means that your connects are a source instead of your requests being a source, your HTTP gets being a source. You can invert it. I don't know how. I need to be able to say that more clearly. I'm deciding whether to introduce this here. There's this library called Cycle.js. It's built using reactive extensions for JavaScript, which is another implementation of the same pattern, but in JavaScript. And the Cycle.js pattern builds these simple functions, and they allow you to build a continuous loop. And it was originally designed to work for UI, so that you would have your inputs from the UI going in as sources and the outputs going out to the DOM. And so you end up with this continuous loop of these streams where the ends are connected together into a loop. You can do the same thing for the server. You can have this loop, and I want to build this in C++, and I started once, and it requires variants and things that I didn't get to it yet. But you can build this loop so that your requests come in, and then the result is the response to that request going out, and it's just this loop of streamed operators from one end to the other.
Thank you.
What's a cold observable, and how is it different from a hot one? From the slides about testing observables.
Oh, cold and hot observables. Yeah. Yes, that is a common topic in reactive extensions. It's one of the more subtle things that people have to accustom themselves to in this model. And it comes up pretty early, like you kind of have to just take it on. I didn't talk about it yet, but I will now briefly. Your mouse is hot as a source. Even if I'm not listening, mouse events are still occurring. And nothing is remembering them. Depending on when I attach, that's the set of events that I see. I don't see the events before I attached, and I don't see the events after I disconnected, of course. And if there's any gaps between times that I attach, I miss those things. So that's a hot source. A cold source is like all of my ints ranges that we're just counting from from a first int to a last int. Those are cold. Every time I subscribe to them, it starts over at the beginning, I get every single value, and then it ends. Hot and cold is just the terms that were used to describe these two types of sources. And so there are ways to take a hot thing like a mouse events and turn it cold, and there's ways to take a cold thing like those ints and turn it hot. And what that means is that when you turn a cold source hot, as many people as you want can subscribe to the same source now, but they only get the events that arrived since their subscription. So everyone observing that thing could end up with a different set of outputs.
Thanks.
Mm-hmm.
Thank you for your talk. Could you please explain lifetime management in your algorithms? Because I was surprised that you haven't any object that controls the lifetime of this async stuff. Because, well, that's it.
Yes, that is very true. There is an object that controls the lifetime, but it's not an object that, it's a shared object. So it's the subscription object. So when you subscribe in RxCPP, you have to pair a subscriber and an observer. And that subscriber pairs an observer and a lifetime. The lifetime is the subscription. So the subscription is internally a shared pointer over some state. And all of the algorithms end up with a copy of the subscription, of the lifetime. Yeah, the subscription, the lifetime. But it's also returned from the subscribe method on the observable. So once I've bound the two together, the resulting lifetime is returned to the person who bound them together, who started, someone has to say to the sender or the observable, send everything that you have to this subscriber. The thing that returns from that method is the subscription, and that subscription has a method on it called unsubscribe. That unsubscribe method is also called when the stream ends either through an error or through the finish, like the source finished sending values and it sends down the completion event. And when the completion event finishes, the unsubscribe is called. So lifetime is always ended automatically by the end of a stream or by an exception in the stream, an error in the stream, but it can be prematurely terminated by anyone else, like anyone else that has this shared object.
Yeah, but for example, there's a lot of streams, mouse move, sockets that exist for a long time. Mm-hmm. So if, for example, I subscribe to mouse moves and print them to logs, and then I want to stop it. I don't see in your slides that you keep that subscription object. You just omit it after subscribing. Is there a way to keep that subscription object and then unsubscribe from this async loop to stop, for example, printing events to logs, and so on? So the subscription object is returned from the pipe operator, isn't it?
If the last in the pipe is subscribe, then the result of the whole expression is a subscription. So if the last operator is subscribe, then the result is a subscription. It's actually possible, well, if you look at the actual code, you'll see that I am using the lifetime, because when I switch out of a particular slide, I want the previous thing to stop even if it hasn't finished. And so my exit from a slide in the JavaScript actually tells the subscription to unsubscribe any live operation. And then I'm able in the next slide to start the next one with a new lifetime. And so you can't see that code in the slides, but if you look in the actual code on GitHub, you will actually see that I'm managing the lifetime of each of these things explicitly by the slide transitions.
Okay, thank you very much.
I guess we need a new mic. I missed the first part, sorry. Hopefully that microphone will work.
Hello. My question is how all these lambdas allocates and how to store their results.
I see. So the lambdas are just function objects. So they get stored in the state for the operator. You saw how they were being passed through in the early. How easy will that be to get to? So the predicate is a function object, and it's just being passed down through the lambdas in this particular implementation as a part of each of these contained lambdas. So essentially you end up with some copies of the predicate in this implementation, which of course was using as simple of a syntax as I could for the slides. You own this implementation. You can be as efficient as you want about how you store the incoming lambda. But the key is that this function could be called with different destinations. And so you need to keep a copy of the lambda for that, and then keep a copy of the lambda for each one of those destinations. Presumably with move semantics, it's not going to be too much overhead, but again, you completely control the implementation of the algorithms, and you can be as efficient as you want in building. Like, you don't have to use lambdas in these. You can actually use full function objects, which is actually how RxCpp is now, because it actually runs in C++ 11. It doesn't require C++ 14. So in in RxCpp right now, they're actually full function objects. And the part that I find unpleasant from an efficiency point of view in the current RxCpp is that each of them is using a shared pointer to hold its state. And I would much rather see the subscription own the state without any shared pointer blocks or ref counting or anything like that for all of the operators in a particular segment of the expression. So that's why I implemented it that way in here for the toy implementation, so that I don't have to separately shared allocate in each of the operators. That implementation and the subscription can even get more intelligent if it wants to in the future, and do some sort of heap allocation of its own, so that it's not even going to the main heap. It could get as complex as it wanted to.
Hello. So thank you for the talk. And I was a little bit late. I'm sorry. Maybe I will repeat the question. But can you please maybe to clarify the difference between subscriber and observer one more time, because it was a little bit tricky for me. Thanks.
Okay. In ArcCPP, a subscriber is the thing that pairs the lifetime with an observer. So an observer only knows how to respond to the next error and completion signals, and then the subscriber is what pairs it with a lifetime. So you need a separate lifetime for every call to a subscribe method, and that's why the subscribe method takes a subscriber instead of an observer, so that you can add this lifetime component to each call.
Okay, thanks.
Sorry, another question. About a subscription object. It doesn't from your code. It doesn't seem to be following RAII idiom. So if you just omit the subscription object, will the chain be broken if you just omit the subscription object? Does it follow the RAI idiom?
So I'm not quite sure what you mean by omit the, you mean if the design didn't have a subscription object in it, if it only had the receiver or the observer and the observable?
I mean, if I use a operator pipe and then
Yeah.
I don't store the result.
I see.
Yeah.
So the RAI pattern in an async domain has to do with the lifetime of the source. So when the source calls completed or error on on an observer, that's the point at which the lifetime ends. As soon as a error is reported, the return path from that, the unwinding of that stack, will call the unsubscribable into the lifetime. Because there's nothing, it's part of the contract that, you can have a whole bunch of calls to next, but you can only have one call to error or one call to completed, or you can just have a call to unsubscribe, in which case neither error nor completed get called. So unsubscribe is a forceful early termination. Natural termination is through calling the source, passing down a completion or an error, and that will also kill the lifetime.
Okay, I get it. But in your examples, if I just pipe one source to receivers and subscriber, then I just forget the result, the subscription value, the object that is returned from the pipe operator. Then if I forget this object, I have no way to stop this async algorithm preliminary.
You have no way to early terminate it, but it will stop on its own when the source finishes. For a mouse source, it won't stop. And so that's an issue. If you have a mouse source, you have to keep the subscription so you can terminate it when you're done with it. But for, say, a network connection, eventually, the connection's going to break, and that would naturally terminate it, even if you hadn't explicitly unsubscribed it.
But connection can persist for a long time.
It can.
Yeah, but maybe it's possible to replace the subscription returned from the operator with some subscription holder that just calls and unsubscribe in destructor.
Well, subscriptions are nestable. And so what you can have is you can have a subscription that you keep, and that's actually essentially what I did in the implementation of the slide transitions. You keep a single subscription, and then you use that subscription. You can either nest other subscriptions in it, and then one of the options for subscribe, of course, is to pass in the subscription that you want to use for that particular subscribe, to control the lifetime of that particular subscribe. So you can actually share the same subscription across a whole bunch of calls to subscribe if that's actually what you wanted. Or you could have a separate subscription for each one of them, for every subscribe, and nest it into some parent to begin with. And now all of them are independent unless someone kills the parent, and then they all go down.
Okay, I get it. Thank you.
Hello. Maybe I'm completely missed the point, but I've noticed that all your pipelines are linear. So the first question is whether they could branch, something like parallel composition operator. And second one is, what should I do when I need some kind of parallel processing, not sequential one, here? Some kind of dispatcher of events. Whether it's useful here or not, I'm not aware, because it's some kind of proactor or reactor pattern, which one I could not remember.
See. Yeah. So any case where you have some state that you want to maintain in from a stream of inputs that are arriving over time, you can use scan or you can use reduce, so that as the events are coming through that you want to process, you're using them to update whatever the model is. And in this case, the model could be a file handle. So you can use your events and have all these algorithms providing the coordination of the events to make sure that the right events come in transformed into the right shape and at the right time. And then once they arrive at your reduce or your scan or whatever, you can use them to update a file with the current state.
Yeah, but it's an example of still sequential processing. I don't know whether parallel processing is useful here in a complete model.
I see. Okay.
But for event-driven simulation, for example.
Right. So, two things. Yes, parallel processing is possible in this model, and I will come right back to that. First, parallel isn't the... Parallel, in my mind, is a space in which you want to utilize every single available resource on your machine to accomplish something in the shortest amount of time possible. This is for a different scenario. This is for concurrency, coordination. So it's when you want to use the absolute minimum number of resources on a machine until there is something to do. Now, you can still do that in parallel, and that's where I'll get back to what I was putting off. Each of these observers has to follow a particular contract. Those calls to next and complete and error get very difficult to handle if you have to worry about threading.
For example, termination, yeah?
Especially termination. And so what the implementation of the contract guarantees is that at any one time, a particular individual receiver will never see more than one thread on one of those methods. There will never be overlapping calls to next. There will never be overlapping calls between error, complete, or next. That's part of the contract. Another part of the contract is once error or next is called, there will never be another call onto that. You'll never have to worry about seeing a next after an error. It just won't happen.
Implementation.
Exactly. So the goal is to make all of those complexities handled by the implementation so that the users of them have a mental model that is rational and
it's rather complex already. So
yeah. And so to get back to the parallel portion, each subscription has its chain of observables. And within, for each of those, so if you want to have actual parallelism, what you would do, say, if you were parting out a sort, which you would never do in this because it's not really for parallel, right? You're always going to get better performance out of a parallel sort than you would out of doing it here, but you can. You can take your inputs and you can parse them out into groups with the group by operator, and each of those groups you can tell to run on a different thread. Those schedulers allow me to provide threads to each of the groups, which are different threads. And each of those will be able to run concurrently because each of them has a separate observer, right? And so it's just by making a single stream, and that's exactly what I did with group by, into multiple streams. Now each of those streams can run in parallel, and then at the end I can pull them all back together with a merge and get my result out, or a scan, or a reduce. Any of those will let me pull them back together into one result on a new thread, essentially. Like I will tell it to transition at that point so that that observer coming out of the bottom has only one thread calling it, ever.
So I could branch them on the source point, but I could not merge them.
You can merge them because you can pass
between
merge
threads.
a scheduler.
Oh,
And so it's
merely by
getting
my synchronization.
any of these operators that's taking multiple streams as input has to be able to take a scheduler so that it can merge them into the output stream.
I see. Thank you.
Mhm.
Thank you very much.
Any other questions? If not, I will release you early. Thank you very much. Spasiba.